of you and the distinguished panelists and Mr. K.L. Batra, my friend, and also the organizers, Mr. Suzan Sunagar, and the convener of this program, Mr. R.P. Pandey, and Mr. Sethi, for the kind invitation for me to deliver this lecture. I hope you can hear me.
Yeah.
Okay. So it is indeed a great pleasure for me to share the kind of experience we have in developing the innovative coatings for mitigating corrosion in diverse conditions. I use the title diverse conditions because, the title of this particular conference is on surface engineering. And very nicely, Mr. Narayan has said in his inaugural lecture that surface engineering covers wide gamut of engineering the surfaces. And it is many times, it is not sufficient to have just the corrosion resistance. When you give a coating, the coating need to offer resistance against multiple type of failures. Corrosion is one among the failures, and these failures can act in synergy. So what I'm going to do and today is just give you a perspective. I don't think there is enough time to talk about it. Just give you a perspective as to how, as we scientists or engineers are enamored with the diverse type of coatings available for us, how we can engineer the coatings. I also, from the academic institution, I also going to throw some information about how we can achieve these properties by tailoring these surfaces, by understanding these surfaces. And to start with, when you talk about coating developments, traditionally we talk about the performance, how long the coating will last in a given condition, actually, given temperatures, pressures, environment, and so on. Just in cost, we talk about life cycle cost. But of late, this has become a problematic thing. A lot of things are happening over a time period. The so-called excellent coatings, very cost-effective coatings, are not really going to be useful for us. For example, Mr. Narayan talked about inhibitors. Flumates, excellent, very cheap, but you can't use them. People talked about using phosphates, and phosphates are really having some problems. So I'm going to talk about some of these issues, how we evolve in our time period. Coatings having high performance, affordable cost, and also to satisfy the environmental demand regulations. Now, this has been talked to you what corrosion is all about. I just wanted to say that the corrosion, when you talk about the failure due to chemical environment, and the corrosion need not lead to a loss in structural integrity, any loss in function. As Mr. Narayan talked about, heat transfer will be a problem. Tubes are intact, no leak, but there's a problem like that. So that's one of the things. And these things are happening because you have a material, the environment, chemical environment, the design coming to pictures. There are several ways in which you can mitigate corrosion, and coating is only one of the ways of doing it. In fact, coating is one of the predominantly used methods of preventing corrosion because it is very versatile and it's easy to apply in many cases. And surface engineering, we talked about, this is creating a synergy between the substrate and the surfaces. You just have wonderful materials, like have high strength, high creep stuff, all kind of mechanical properties. They don't have good corrosion resistance. Coatings have very good corrosion resistance. An example is glass lining, right? It doesn't have any strength, any toughness, but gives excellent corrosion resistance. Applied over a simple steel surfaces can give you fantastic properties. So it is a synergy between a substrate and the surface that we are going to modify by various means. That cannot be offered, not given by any of these two in isolation, not possible. And when you talk about corrosion, it is quite diverse. I mean, the application is very important. When I talk about impeller, yes, you need to have A corrosion resistance plus impact, turbines, maybe gear, and so on and so forth. These are just a few examples. For example, gas turbines, steam turbines, they are totally different kind of situations. So the kind of coatings that you're going to develop or apply are not going to be the same. They should have different properties. Now, this is a very old slide, so to say, 2010. I think Alan Matthews is chief editor of Surface Coating Technology. He summarized nicely what all the type of surface engineering technologies available for us. And painting, you see here, is one of the important part of this, no doubt about it. Then comes electroplating, zinc coatings. There are various other things like surface heat treatment processes, anomaly. There are several techniques, hard phasing, for example, post in preheat treatment processes, anodizing. Several of them constitute the surface engineering processes. And many of them synergize the required properties, heat, corrosion, erosion, temperature, all kind of stuffs. Various kind of techniques available for us. Now we have a range of techniques available for you to obtain. One property which I call them as hardness property is one of the important properties whenever we talk about a structure which is having a relative motion with respect to the environment it is handling. So you need to have a high hardness. Variety of techniques we don't have time here to talk about. We can give coating thicknesses in the range of 0.1 micron to millimeters. Surface hardening, for example, well coatings, overlaying, well overlay coatings, plasma coatings, they all lie in the thick regions of this section, right? Whereas talk about plasma ion implantation, they are talk about microns or body implants, gears in watches. Of course, nowadays you don't use these kind of watches. Nitrocarburizing, a variety of things are available for us actually. Okay, and so these are the techniques. Again, as I told you, we don't have time. I'm going to give you some kind of exposure for you to get an idea about what are the ways and means that we can achieve better surfaces to have corrosion resistance along with other required properties. Plasma nitriding is one of the techniques very widely used. I just give some example here. Again, not much details. What I'm going to give in each case is one PhD student work. I'm going to give 3 slides. I'm not going to give more than that. So those I'm going to compress the work. The idea is to give you feel for how to generate surfaces that can give you better corrosion resistance. This is plasma nitriding. One PhD student worked with us. Plasma ion immersion technique. Another student, PhD student worked on it. This is for stainless steel. Stainless steels are excellent materials for corrosion resistance, right? But then they don't have, they're soft materials. Where, for example, you're going to use a wall, in a flow lines, you may not be happy with just corrosion resistance. You need to have higher hardness, higher erosion resistance. It's very important. How to do that? You use this technique. Again, we don't have much time. You can implant nitrogen into the material, like carburizing, for example. You can have nitriding processes. You can do that. You can increase the hardness very significantly, starting from 250 weakest hardness to about 2000 hardness. You see, this hardness can be significantly improved by putting nitrogen in that. Actually. But there are some issues that only we, as engineers, should be aware of. You keep increasing the hardness, you might compromise on corrosion resistance of that. So that means you need to optimize the treatment processes so that you're not going to lose corrosion resistance, or rather you're going to increase corrosion resistance and also going to increase the hardness properties. This is something which we talk about the electrochemical polarization curve. It talks about how good it is. For example, what's shown in this curve is potential versus the current. What you see here is when I raise the potential, the current does not increase. We call them as a passive region here. See, so nice. The stainless steel has got a huge amount of passivation that taking place because of this. Again, not all the stainlesses are same, right? 316, 304, and manganese containing stainless. Not all of them behave same manner. So that means we need to understand what is the constituent of these stainless steels and how effective it is when you are going to add nitrogen. Not all of them are there. So we need to do deeper studies to get to know the synergy between what you add to it and then the metal that is going to be there. So this is one way of improving the corrosion resistance plus the hardness of the section. But then the thickness of these coatings are very small and not very large. For example, you can go for body implants, small coating thickness, fine. But I want to talk about the gearboxes where the thickness of the coating is quite large. Then plasma ion implantation will not work. Then you go for plasma nitriding technique. That is there in the Plasma Institute in Gujarat. In fact, it has been helping aerospace industries, even oil and gas industries, thermal industries, nuclear industries, for example, they're helping to a large extent to convert the surface into a hard surface and corrosion systems. You see here kind of coatings, you can call it nitriding processes. This is called plasma nitriding, and this is called plasma nitrocarburizing. Okay, so that's what you can do that, right? So you can get the hard surfaces here, and these hard surfaces have unique properties of hardness as well as the corrosion resistance. I can increase the hardness values, okay, but again, there are various operating conditions, temperatures, concentration of the species that are going to add to it. A lot of variations are going to be there. The net cell, it is possible to tailor the surface to have different hardness values, and then a corresponding change in the corrosion resistance of the section. It's possible. Again, we go into details about understanding the phase transformations, whether nitrogen is in solid form, whether it's forming a carbides and nitrides, all kind of stuff. So we're going to look at it. If you don't do a proper thing, it can be disastrous. You can have nitride, you can have pitting chemicals. So you can optimize it, study them in details, get them optimized properties. So that is about stainless steels. Now we look at materials. Just now, I think probably Mr. Pandey was talking about titanium, aluminum, magnesium. These are very good materials, but they're very soft. How do I improve the hardness properties of this? In case, if you do this technique, the hardness of the surface can be as good as boron nitride. And boron nitride is one of the hardest things, very close to diamond, right? I can increase the hardness of this by using a non-conventional anodizing process. We call them as plasma electrolytic oxidation process. It's very, very simple, environmental friendly. You don't add any chemicals. Very few chemicals are added to it. You just get a very, very hard layer. Look at the layer here, very thick aluminum oxide layer. It's formed, and this layer has got hardness, which is very close to boron nitride, very close to diamond. And correspondingly, the corrosion resistance is significantly improved. Look at the current here. What you see here, the potential versus current. There's a few order of decrease in the current is taking place because of this coating. What more you want? You want a very high hardness. You have excellent corrosion resistance obtained for very soft material like aluminum. This case is a magnesium alloy actually. So you can get these kind of properties. So that is about surface conversion coating. Let me go to some examples of metallic coatings. You all know about hot dip galvanizing, right? Very, very well-known things. People talk about pure zinc. And pure zinc coating is not really pure. It has got about 1% aluminum is there actually. For various metallurgical reasons, they add this. And this is very widely used. But then you can significantly increase the corrosion resistance by alloying with aluminum, like 5-8% aluminum called Galvalum, 55-8%. And we talk about, Mr. Pandey was talking about offshore conditions, excellent coatings, offshore conditions. Galvalum is excellent corrosion resistance material actually. For automobiles, they've been talking about it. We talk about zinc, aluminum, magnesium coating. It gives you 5 to 6 times more corrosion resistance than this one by adding aluminum and magnesium. Superior coatings are being developed by changing the metallurgical properties. Again, I'm just giving you only illustrations. I don't have time to go into details. One of the important things when we talk about zinc coatings is the life of this, the service life of these zinc coatings is related to coating thickness, right? When the coating thickness increases, the service life increases. But that is very interesting that we know about it. But look at the steel industry. The steel industry has to increase the thickness of this by 1 micron. For example, let's take Tata Steel. It has to increase 1 micron thickness of zinc, spend a few crores, maybe about 20-30 crores annually. They have to spend more money for the same coatings. Can we reduce the thickness? Can we improve the properties? Can we have better properties? Because we have no resources of zinc. Zinc is increasing the cost and so on. So can we have thin coatings and have excellent corrosion resistance? And that's where you see here. The example in this left-hand side diagram is average corrosion loss versus exposure time. Zinc is you see the loss in corrosion, and you have zinc aluminum, and you have aluminum here. Aluminum, of course, is a problem, pure aluminum. sometimes it can backfire, giving rise to galvanic corrosions. What we have done in our own lab, in a PhD student, it has been now patented, and we have now transferring this technology to Tata Steel soon, is to develop an alloy wherein you add just about 0.028% element, only that much, right? You can bring down the corrosion resistance so significantly. I'm giving you only a simple diagram for you to appreciate it now. This is for pure zinc. This is the zinc normal, hot dip galvanizing coatings, alloy A, alloy B coatings, 0.028% only element added. Look at this, 168 hours rusting here. Now 552, no rusting taking place. Look at the kind of increase. Not only 552, you can look at this, it has reached almost 1056 hours, and you don't see much increase in the corrosion, corrosion of these coatings. So you can simply tweak it by adding small element. How does it happen? This is the kind of visual pictures that you see here, but see them in the microscope. You see a significant change in terms of the microstructure in these alloys. And this is what we call as a grain size refinement taking place. And this refinement has given enormous resistance to the corrosion. That means you can imagine that same thickness of the coating, life is increased by 5 times, 6 times. Wonderful thing. You save resources, and it gives you better properties of the section. In fact, these coatings, they do not give you, this gives you mirror-like finish. The appearance is really wonderful, actually. And again, the grain size, I'm going to skip. I know the time is going to be short, so I'm not going to talk about more on that. Let me now come to the topic very close to many of you. We talk about paint coatings. The paint coating is one of the problematic coatings. Of course, very versatile. I don't think there's any coating which is as versatile as a paint coating. Actually, it's just easy to apply. But over the time period, a lot of legislation. The olden days, people talk about chromating. Then comes the phosphating. Now even phosphating is being replaced. That means we talk about some kind of primer coatings where you don't want chromates, you don't want phosphates. So people talk about coatings based on silane-based coatings. We have done this work. This Franz Gaonkar, a doctor, postdoc candidate in our place, we've done actually. It's an eco-friendly coating, simply silane, silica. Silica is to be as friendly as possible, because you have a lot of sand, so it's environmental friendly. Of course, you need to modify with various kind of ingredients you add to it. Actually, you add this, and you can add more. Now, what I was talking about is, in Europe, for example, phosphate is now known. Just not only chromate, because phosphate is a good nutrient, right, for the plants. So you can see this eutrophication is a problem for pure water resources. So that means the challenges are more as the technology becoming more and more developed, as the resources are being shrinking, and there are a lot of legislation to not use the normal coatings for that. So this is the kind of work that we have done. It's work done with the Tata Steel at Europe. We undertook a work on it. Now, one of the things that we talk about is you can never forget science, right? Now we look at the elements which are going to be very close in terms of properties, like a phosphate or maybe chromate, for example. We look at some elements. These elements are like titanium, niobium, zirconium, lanthanum, and so on. So you look at incorporating these oxides into the paint systems and see whether we can improve this property of this here. So this is one of the work that we have done actually, and so that was one work is done for the automobile industry, because automobile industry is one of the polluting industry. A lot of in fact, that is one of the real problems in terms of pollution as compared to other industries. So silane coatings, again, we can look at various types of silanes, the stability of the silanes, their ability to hydrolyze, the temperature resistance, all kind of stuffs. Again, these silane coatings sometimes can crack. You add some nanoparticles, you add some cerium, because cerium gives you something like intelligent element to reduce the corrosion whenever there's a crack occurs. So these are the kind of things, they look at these coatings. They are very, very thin coatings. It's very transparent coating, for example, and we can add various kinds of additives in order to improve the performance of the section. Okay, again, visual observations, and see, these are it's like a lacquer, you see. You can have a transparent coating, and then you can have an excellent corrosion resistance. This is called as impedance plot, Bode plot, we call it. Actually, 10 power. See, look at the normal coating, normal, uncoated mild steels. It's about 10 ohm centimeter square, 10 power 5 ohm centimeter square. So that is the kind of high orders of resistance is increased because of these coatings. Again, excuse me, because I'm not going to details, no time. I'm just trying to illustrate to you how you can develop newer coatings, which also complies with the environment actually, and also can give you better performance. Now, come to let's say paint coating, so-called polymer coatings. I give you some two examples, then I close my talk. Now, we all talk about VOC. Now, that's why we talk about water-based coatings now actually. Can we really use the so-called polymer coatings and try to avoid VOC, volatile organic compounds? How much you can renew in physics. So this is one of the work of our PhD student. It is done by, it's also part of naval work for DRDO laboratory. Now this is basically utilize low density polyethylene, and Ms. Batra will know that low density polyethylene is very good, but then it cannot bond so nice. It's not having a polar group, right? It doesn't have a polar group. The bonding is not going to be so great. So what we do is that we take this low density polyethylene and then graft a molecule that will form a bond with this molecule, and which in turn will bond with the metal surface, right? So you can graft this in space. I'll show you later actually, so that this molecule can be made into polar molecule, and that polar molecule is going to form a bond. Now, what is the advantage of this? This low density polyethylene granules, you can do a thermal spray now. You can do a thermal spray. And when you do a thermal spray, they don't decompose. Very nice. They melt it and form a kind of compound. Now look at, this is the kind of comparison between the cost and VOC and all. We don't have time. I can share the slides with you later. All I'd like to say is that cost is good. Yes, good life, low VOC. That's the kind of thing. And then of course, this is the kind of way that you can change the technology of applying the coating itself actually. Now, as I told you, we start with the low density polyethylene, and you tweak the molecule by grafting it with malic anhydride, malic acid you call it, because malic acid has got a polar group. You just incorporate that into this molecule, and then what happens? That becomes a polar group. The polar group gives you what is called as a bonding with the metal surfaces, and then apply the flame. So there are a series of methodologies people use. There are various ways where we are grafting it. You can graft it using extrusion thing. You can graft it using gamma radiations. We finally did with the extrusion process actually, so that we can blend it very nicely. And of course, we need to understand the molecule. What really happens is when you're going to graft it, as that anhydride gone to the molecule now, yes, it has gone to the molecule, to show that yes, there is a change in the hydroxyl group taking place. You can reconfirm this in terms of looking at the acid values. LDPE 0.6, LDPE malic acid grafted is, you can see 8.9. So it means there is a component of malic acid which is being grafted into the molecule, actually, the polymer molecules. So we can also look at it. Now again, when you do a thermal spray, it should not decompose, right? It decomposes, everything is gone. So you look at this spectrum, the IR spectrum there, before and after that, and see that, yeah, they're looking good. I mean, there's not much of a problem, and there's no decomposition. Of course, we need to optimize the temperatures, we need to optimize everything. Otherwise, you can burn. I mean, obviously, you can burn. So we need to optimize the process conditions so that it is going to be just melting and forming coating and all. It is just not enough to develop a molecule. You need to look at the characterization. For example, you have a polymer. How does it resist corrosion? It doesn't allow the water permeation, right? So we look at what is how much of water is getting permeated into systems. So you can use various techniques. One technique is IR spectroscopy. We use impedance spectroscopy to determine the amount of water that is being converted into that. So we also follow these peaks over here, which are indication of to what extent the polymer is getting degraded with time. Now, you can quantify the corrosion resistance properties. Look at this value here. We call it as polarization resistance offered by the coating for the flow of current. Mr. B. Narayan talk about current has to flow, right? How does this coating offer resistance? You can see this coating here. The 10 power 10 ohm centimeter square. It's a phenomenally increasing thing here now. So in this thing can happen, okay, because of grafting of the coating. Of course, this has been added with what you call red oxide. Pigments are being added to this particular coating. Into that, again, you can determine the amount of water that is getting permeated, right? We can do this kind of things. You can see that, in fact, it's very interesting now. The water permeation in this coating changes with the pigment concentration. At this concentration, the pigment, the water permeation becomes the least, you can start increasing. Of course, there are science behind it in terms of how the pigment itself becomes a path for channeling and so on and so forth. Okay, so up to this level, it becomes a block, and beyond this, they themselves forms a continuous path for the water flow into the coating at all, actually. So this is the proof of the pudding is in eating. Then you look at these coatings, put them to salt spray and see what happens at all, and look at the blister formation in a salt fog test. Okay, we have various kinds of pigments, titanium dioxide, and you have MIO, you can use aluminum. Various type of pigments are being added to it to determine the performance of these coatings. This is a kind of don't worry about this table here. This only tells you that we have done a detailed studies in terms of salt spray, seawater immersion, humidity, because the performance of the coating in salt spray, salt fog is different from the immersion conditions, right? So we just look at what are the ways that is getting performance is done here. This is in terms of scale. These are all published, and I can share the data with you. You can go through them very, very leisurely. Very interesting thing about is that the kind of pigment that it add to it plays an important role. I think one of the distinguished panel member talked about nano, right? These nano pigments is very important. We just looked at the role of nano clay composite, closite 20, right? It's a clay actually. And when you add this clay, you look at the water absorption. Look at this y-axis, volume of water absorption versus exposure days. This gives you the lowest amount of water absorption here. That is due to the addition of the clay here, right? The clay addition reduces the water absorption and so the performance of the coatings. And this has been now proven. This coating has been applied and shown, and we have also been published here actually. So this is a technique, a technology. It's developed in India for Indian applications now, and this is eco-friendly coating, and it's very, very economical coating as well. I have two more topics. I think let the chairman please let me know when I need to finish it. Give me just 5 minutes time, and so that I can wind up my talk. See, it is very important that we understand the molecule and try to tweak it so that you get the required properties. I give an example. This is the PhD work of Rasmi David, my student. She's finished PhD and is working now. Now, Mr. Bode was talking about in 1980s and 90s, people talk about epoxy-based coatings. Epoxy coatings are wonderful coatings at all. But one of the problems with epoxy coating, typical epoxy coatings they are brittle. The toughness of these coatings are going to be not very high. I don't think I need to talk about the importance of the coatings, how it's being applied. It's applied by two-pack thermoset resin processes. I will not go into details about this one. Let me just go into what our work is and how it fits into multi-requirements. And this is related to submarine applications, underwater applications. Now, when you talk about cases where you talk about splash zone, we talk about cargoes or platforms, and we talk about cases where constant impingement is taking place, the paint has to last its life before it can protect for longer time. Okay, so it is necessary to have corrosion resistance, necessary to have chemical resistance. It is important to have mechanical resistance, especially toughness. And the epoxy coatings are not known for that. So how do you really modify this? The epoxy has a very strong cross-linking, right? When you have more cross-linking, it's very rigid, no doubt about it. It's not tough part. So how to do that? You just get into fundamental aspect of it. We borrowed something from the aerospace industry where people use polysulfide, right? Polysulfide is linear chain polysulfide is used. It's an elastomer, for example, right? It is used as a gasket and so on. So can we incorporate this polysulfide into the epoxy? Okay. Can we incorporate carboxylic terminated polyethylene glycol adipiate. Now we synthesize this particular CTPA. We synthesize again carboxylic terminated polyethylene glycol succinate. We synthesize these compounds and then we cross-link along with the normal epoxy actually. What is the advantage? These are linear chains. They are almost aliphatic now. So that means you have a combination which is aliphatic, which is having a good, resilience. In this case, for example, you have here, whereas aromatic, you have much more cross-linking, you have brittle structures. So you can put them together, then the molecule will have a better toughness. And I'll show you some of the data that we have got from this now. And again, you can see how by modifying this, again, systematic work, various proportions of these additives are being added, and then the corrosion resistance are being determined in this case actually. Okay, so again, this is the plots of this is unmodified epoxies and modified with these two things. After, please look at this is after about 1,000 hours of exposure, right? About 1,000 hours of exposure, you still have 10 power 6 impedance actually in that. That means it's really good. It's really good, and so the performance of this is certainly very good, no problem. Okay, in terms of corrosion resistance, and again, of course, this summarizes the data that you see here, right? What you see here in this the case is you can see that the resistance of this coating versus the immersion time. You can see this 10 power 9. The decay is not going to be that sharp. Okay, and the neat epoxy, you can see that there's a sharp decay in terms of resistance here, right? So the modification of this molecule with these additives now, I think, has given rise to a significant improvement in the corrosion performance of the epoxy now. There are something like breakpoint frequency, too much of science. I will not, dwell on it actually, but these are some of the techniques which are useful to really understand the coating properties without taking into consideration thickness. You need to normalize. For example, you have panels of different thicknesses. Obviously, the performance is going to be different. Can you have a parameter which will take into account, for example, the thickness? That is called as the breakpoint frequency. You take this value and then try to understand how the performance of the coating is really changing. Okay, so among all these coatings, this is adipic acid has given us to a better properties than this actually. Now these are the data with respect to the elongation. Please see here the elongation of this particular polymers. This is all the freestanding films, epoxies. Look at this now. This is the elongation to break, tensile strength, right? Now you see this elongation to break. This is your, this is modified polymers. So look at this here. Now the elongation has increased from 87% to 168% here. That means it's having really good toughness as compared to the neat epoxies. Of course, when I'm going to increase the elongation, you are going to lose on strength. Of course, strength is going to be lost. But in this case, you can see here the strength is still better as compared to the other two modifications. Well, I just want to touch upon last, if there's a time permits. When we talk about coatings, many times we talk about coatings for ambient temperature applications actually, or we talk about elevated temperature applications. Elevated means we talk about 200 or something like that at chimney. But there are temperatures like gas turbine applications. Whole lot of technology. In fact, the technology is so highly advanced in terms of developing coatings for gas turbine engines. And these are very important because the efficiency of these engines depend upon the operating temperature of these engines. If temperature goes up, then of course there's a creep problem, oxidation problem, so on and so forth. The coating should have thermal barrier, corrosion resistance, shock resistance, all put them together. Now, over the years, again, it's not a very recent slide, it's around 2000 years, the increased temperature of operation. You can see this here, over from 1960 now to that, about 250 degrees Celsius is a rise in temperature of these turbines being operated now. So that's the kind of advantage of having these coatings. But these coatings are developed by plasma spray electron beam processes. Each of them have advantage. I have about 3 to 4 students work on it actually, but I just again give you only one slide to show how important it is to develop a technology that will have better performance. These are all the turbine blades that we talk about, gas turbine blades, and this is coated with an oxide coatings. There's a thermal mismatch between this metal and oxide coatings. In order to reduce the thermal strains, you have a bond coating, which is having a coefficient of thermal expansion lies between this oxide coating, the metal coating here, the bond coat, and this gives you a nice graded performance from the point of view of thermal expansions. Now, the point here is when you're going to cycle the temperatures and there is going to be strain involved in these coatings, that means the strain has to be tolerated. How do you tolerate the strain? You tolerate the strain by growing these oxides in a columnar manner. Please look at this. There is aligned growth of these oxides. And because of this aligned growth, when they start moving like that, the strain is now taken care of. They don't really break. But then there are some issues here because these grains allow the corrosion liquid go inside. There are some problems. Okay, so that happens. So how do you really modify this? We work with ARCA Hyderabad and to modify some of the coating. Oh, I didn't have this slide here. It is called as solution precursor plasma coatings, for example, that gives you better strain tolerance, better resistance against oxidation, sulfidation, hot corrosion, so on and so forth. This is a big topic by itself. Okay, it's not having time to do that. But all I'm trying to say is that sky is the limit. I mean, you just only have to apply the technology in order to develop coatings and surfaces that will have far-reaching properties. So I think I need to be thanking or acknowledging the many of the students here. Several of them are not given here. Mostly we are given only PhD guys who are all contributed to this. There are several funding agencies. Main funding agency was the Department of Science and Technology. So with this, I would like to end my talk. And again, I would like to thank the organizers for the kind invitation. I do hope that this lecture gives you some kind of exposure to the diverse coatings, the diverse technologies that are available to solve the myriad problems, various kind of components face in real life situations. So thank you again. If you have any questions, I'll be happy to answer. Thank you.